Hello, my name is AmeAmor Blatchford-Rodriguez, computational data science major at George Mason University. I'm the program manager for the INTI mission for collecting water samples on the lunar surface. Today, we will be presenting the final mission proposal and design. Our team consisted of 3 institutions represented here. Next slide, please. Here's a visual representation of the organization chart of our team with roles listed. We have 2 divisions, science and engineering, with primary leads in systems engineering, entry, descent and landing, robotics, and mission planning. Next slide, please. The objective of the INTI mission is to characterize the polar water ice on Earth's moon, as well as identify in situ resource utilization for the mission, as well as for future missions. The graphic was modeled by Morin in Python and is a simulation of INTI's motion upon release from the orbiter. Key milestones include our launch on October 17th, approach, EDL, and touchdown of the lander, all occurring on October 24th. Surface ops will begin upon reaching the site and last approximately 2 days, ending our primary mission on the 26th. Phase A consisted of building the lander design, choosing spaceflight instrumentation, as well as group data systems. Phase B consisted of cost scheduling, system requirement review, and system design review. Phase C and D consisted of scheduling negotiations, spaceflight systems design and development, integration, PDR, CDR, test readiness review, and budget constraints, and design variation. And lastly, Phase E consisted of configuration changes, data collection, software development, capturing lessons learned, and development of the final mission report. Next slide, please.
Hi, I'm Kimi Medina, a physics student at University of Kentucky. For our landing site, the area had to meet our objectives and be well documented. The 2009 L-Cross probing found evidence of ice and water vapor, so the Cabeus crater is a good candidate. One issue with Cabeus is that the surface area only has 1.1% water content. The ice may be deeper than expected. However, we found a plateau in the lowest and coldest point of the crater for a stable and hopefully fruitful landing. Areas like this one hold volatile cold traps and, of course, ice water.
Hello, my name is Jason Sanchez, electrical engineer attending George Mason University. I'll be talking about the evolution and changes of INTI's mission planning, science, and hardware data. During the initial iteration of the team's preliminary design review, the team's idea was to focus on terrain reconnaissance via human operators driving INTI in day-night shifts. With ground control, INTI would have extracted photogrammetry and reflectivity values as the mission continued deeper towards Cabeus craters permanently shattered regions while documenting all possible data using UHF telemetry. Next page, please. As per science changes, after reviewing adjustments via Descent and Landing's Variable Radius Drum, or VRD, the team adjusted the lander's onboard scientific hardware due to changes in the total weight restriction and soft landing speed requirement changes of approximately 2.5 meters per second to a more flexible soft landing due to the VRD prototype. The variable radius drum prototype should be able to safely operate as a bonus payload and change test platform and shows a survivability impact of approximately 3.25 meters per second. In regards to computer hardware, all data will be transmitted via UHF to send ISEM's data through .csv documents to save power and bandwidth, along with 50 megapixel photogrammetry and ISEM captures onto a 10 terabyte bank of high performance, low watt hour micro SD cards to save on overall power and bandwidth.
My name is Morin French. I'm a mechanical engineering major at Howard Community College, and I will be covering INTI's descent and landing. The main challenge for entry and descent was to strike a balance between our mass constraints and the high necessity of reducing the lander's velocity as quickly as possible. Its initial forward velocity on release from the orbiter is 2.38 kilometers per second, which is also lunar escape velocity. We use a single bipropellant hydrazine thruster for an initial single braking event to reduce our velocity to about 2.19 kilometers per second. After that, we rely on lunar gravity to pull us into a ballistic descent with microthrusters to maintain INTI's attitude, and utilize a system of variable radius pulleys to absorb the kinetic energy of our landing. This protects the payload from the effects of sudden deceleration upon impact with the lunar surface.
Hello, my name is Joshua Ehizibolo. I am a mechanical engineering major at Prince George's Community College. I'll be discussing our payload, the infrared spectrometers for ExoMars, ISEM. Water ice signatures are present at 1.5, 2, and 3 micrometers. The instrument we chose to detect this signature is an infrared spectrometer, the ISEM. It's a pencil beam spectrometer with a range of 1.5 to 3.3 micrometers. With this instrument, we'll be able to detect and distinguish the spectral bands of water ice, hydroxyl, and any other lunar minerals we find within its range. We can see a picture of the ISEM shown, and also a graph showing the reflected bands of water ice and hydroxyl. Next slide, please.
Hello, my name is Aisha Hameed. I'm an IT student at George Mason University. I'll be discussing the payload integration. The interaction between the hardware and the software is made possible through the lander's flight software, which will run off of VxWorks, a real-time operating system. This allows for the processing of data as it comes in with extremely efficient processing times. VxWorks development environment is based on a remote development method, and it's a task-based operating system. This means that applications are organized into independent cooperating programs, and each program is called a task when executing. Tasks for this design will be executed on a preemptive priority scheduling system, meaning that each task will be assigned a priority level, and high priority tasks will be executed first, the highest priority being 0 and the lowest is 256. In VxWorks, interrupt handling does not require for the task context to be switched because interrupts are run outside of the task context. This allows for the processing power and speed to remain efficient. The standard set for this real-time operating system is the Portable Operating System Interface, POSIX 1003.1b, which is designed to facilitate application portability. The layered structure of the operating system is shown here, with the application layer being the real-time embedded applications. Support layer is the graphics, Java support, multiprocessing, POSIX library, and etc. Networking layer is WinNet networking, and then the core operating system is the Win microkernel, which includes both POSIX interfaces and interfaces specifically for VxWorks.
Hi, this is Kimi Medina again on hazards. Our safety officer is AmeAmor. To help mitigate personal hazards, she encourages and guides personal training, equipment and team inspection, as well as hazard documentation. She is an important asset to the team's success. Shifting to environmental hazards, multiple tests were done to ensure that the lander could endure the full mission. Radiation testing was done to mitigate hazards from solar and cosmic radiation, thermal testing for things like extreme heat, 30 Kelvin temperatures, altitude changes, humidity, thermal expansion, and vibration testing for lunar dust impacts as well as EDL movement. Life cycle testing was done on the lander's outer materials as well as its instruments.
Hi, my name is AJ Morrison. I'm an electrical engineering major at George Mason University, and I will be covering INTI's design evolution. INTI's first 2 rover iterations were focused on traversing Cabeus crater, particularly in regions of low light, and the designs were largely impacted by the Curiosity Mars rover. However, the concept for a system of movement proved to be too massive and energy inefficient. It was consequently removed. Designs for a drill arm to retrieve regolith samples were also discussed for both iterations of rovers. However, this concept was also removed as the team decided to solely develop a lander model that would incorporate the variable radius drum system.
AmeAmor here again. INTI's outreach team will consist primarily of the INTI outreach interns as well as volunteers. Listed are planned outreach events for each of the following levels. K through 12 will consist primarily of speaking and demo events held both virtually and in person. Teaching kits will also be a primary modeling tool for promoting future generations in primary education. College and university level outreach will primarily be through partnership events with organizations on campus, as well as national organizations like SHEP, NSBE, and IEEE, etc., promoting STEM retention and participation. Social media updates are also a major part of our missions outreach. It will consist of timeline updates, alerts, reposts of outreach events, as well as bi-weekly postings with infographics, etc. And that concludes our mission presentation. The team would like to thank the LaSpace admin and mentors, as well as viewers of this presentation for their time. Thank you for watching.